So let's put this into a circuit. It's called the Event Detector circuit, created by Rated Technologies, and I put analog in front because it can be used as an analog memory. It can also be used as a digital memory, with this capacitor being either full up or full down. So if we apply a voltage through R1 and went directly to ground here, this RC would act exactly the way we just described, or I just plotted on the previous pages. However, in this case, there is no connection to ground. This diode here prevents the charge from going out of the circuit that way, so it all must go through the base resistor of an NPN transistor to ground. So my R now, these two resistors combined, here's my C. However, this current through the transistor forces current flow here, which pulls down the voltage across the resistor and slows down the rate at which the ferroelectric capacitor charges. So this circuit actually runs slower than a classic RC. So let's follow the charge. Voltage here, charge flowing through resistor, through the ferroelectric capacitor, through the base emitter circuit of the NPN transistor. That base emitter current forces a higher level current through the collector emitter path. And that's this current times beta gives this current. So the resistor is carrying not only the capacitor current, red, but also the transistor current, green. So the two currents combined force the voltage drop across R1 to be higher than it would be if only the capacitor current were flowing through the resistor. This restricts the rise of this output to even longer than it would normally be if I had just the RC. So my rise time is RC, in this case R1 plus RB. It's my RC that we talked about before in the early equations, but it's lengthened out by the beta of the transistor. Now the current flow through this transistor, because it's so low, this transistor is going to be operating as minimum beta, usually around 2 for an NPN transistor. Now in this circuit I'm showing an NPN transistor. This circuit can be reconfigured to operate off of PNP transistors or current mirrors and FETs. Now again, this also follows the RC time constant rule. It's hard to predict what the rise time is going to be for a ferroelectric capacitor because these things are so complicated. However, once you've run this circuit once and you know what the rise time is, the rule is very simple. If I double the capacitance, it's going to take twice as long to rise. If I leave the capacitance the same and double this resistance, it's going to take twice as long to rise. If I leave the same resistors but halve the capacitance, it's going to take half as long to rise. The shape of the curve is exactly the same, just the time constant changes. Now one thing to note is that if I leave V power on long enough, this ferroelectric capacitor is going to be fully charged up. Voltage applied here can do nothing but switch this capacitor up. However, I can apply a voltage at the input and force the capacitor down. So a positive voltage here will apply a positive voltage on this node. Part of the current is going to flow through the transistor turning it on, which connects this point to ground by a short 0.3 of a volt. So the positive voltage here will switch the capacitor down because the positive voltage here, ground connection there. Just the opposite of V power. So you write it down with this input, you move it up with V power. Notice that there's no resistance in this path. So this switch can be very, very fast, even in the microseconds. Because there's only a voltage drop here, we have to add 0.7 and 0.3 volts, or 1 volt here above the saturation voltage for the capacitor. But this can switch in less than a microsecond. This switching time, however, is a function of the size of the capacitor and the size of these resistors. We'll take advantage of that for the analog memory. So let's go back to our memory envelope. The solid black line here shows the rise time of V out, this point of the circuit, if the capacitor is already up when I apply V power for this long. On the other hand, if I put the capacitor down from the input, then apply the voltage of V power, I get this shelf. It looks exactly the same as with just a resistor. However, this is longer by a significant factor because of the effect of the transistor. It also allows us to apply two positive voltages, one to set it down and one to set it up. The black curve is starting from the full up condition. The blue curve is starting from the full down. Now what happens if I don't write the capacitor long enough to saturate? If I'm starting from the full down position and only write for this long, it's going to follow this path and stop. Now this shelf is the remnant polarization, so the capacitor is going to stay at that position. This circuit technique makes it much easier to write an analog state into the capacitor and then read it. Now what's the difference? To get saturation, I just apply the voltage on V power longer. If I want to stop at this point, I just apply a pulse that long on the shelf. If I want to stop at this point, I apply a pulse that long on the shelf. If I get too short, if I apply this level of pulse, about 50 microseconds, I won't even reach the shelf, so I'll never move any remnant polarization, no matter how many times I apply a pulse. So I have to at least get on the shelf to get remnant polarization to move. Now one way to read this is to apply a saturating read pulse or saturating read voltage. So let's say I write to this state right here. I've used up this much shelf voltage. If I then apply a long voltage to the capacitor, to the circuit, it's going to rise, go to the shelf, but the shelf is only going to be this long, as you can see. Then it's going to go and saturate. I can do that at various points along the path. Here's a blue. Here's a blue. I wrote this much of the shelf. This much is left, which is what I have here. However, if I go to this deep purple path, I leave very little of the shelf left. So when I do the long read, I get, this is my deep purple. I get very little of the shelf left. And if I go past the shelf, as with this orange trace, I have no shelf at all when I rise. Another way to do this is to apply a fixed pulse. Now in this case, the pulse is the full voltage, but I'm only giving it long enough to rise this much during the test. But if I apply another pulse right after that, it'll move a little bit higher because it's only starting this far and it's moving a little bit less charge. And a third pulse will move it here, fourth pulse will move it here. Now notice in each case I'm starting the pulse a little bit later, and this is for a visual effect, so you can see how the pulses, their peaks, line up and form the shelf. This pulse has saturated the device, so I can use this 2.5 volts as a reference for when I've gotten past or I've saturated the capacitor, because further pulses just put me up here and there's no differentiation. We got 1, 2, 3, 4, 5, 6 pulses there to read the capacitor, saturate. So in pulse analog operation, I can preset down from the input. I can determine the number of pulses down from full down to full up. Then I know what the saturated storage in the capacitor is. I then preset the capacitor down. I can write in some number of pulses from 0, in this case to 6. I can write it from a controller, like the EDU or a microprocessor, or I can write it from some sort of sensor that sends what's going on in the environment. I can have a retention period, and then I count the remaining pulses in the memory. I do pulses until I pass a threshold, and my stored value was the maximum 6 minus the count. So if I put in 2 pulses, the count is 6, then retain for a while, then come back, only 4 pulses are needed to pass 2.5 volts. So the 6 minus the 4 tells me that 2 were retained in the capacitor.